Hi, thank you all for coming. Thanks Simos and Elif for helping organize this event. It's a cross-graduate event that in a way tries to bring together certain aspects of the way in which graduate courses operate and work in the AA. In this case is the questions of simulations. The idea is that there are many types of simulations in terms of the scale, the approach, the material they work with, and each master works with them in a separate way. And the idea would be to discuss how we do these simulations and what are the different paths that lead from the different models, the different approach to nature, the different forms of abstraction behind the simulation towards the fabrication of design concepts and design discourses. The idea is that, well, this is one event that may lead to other events or perhaps other moments where we also share more ideas, share resources, whatever type of resources those may be. Along the years, and build a bit of a strength, in the AA of how the school, in a way, approaches this type of phenomena. The way this is meant to be working is we will start with EmTech presenting 2 projects with Elif, introducing 2 student projects, then having a couple of questions and answers about those projects. Then LU will be presenting 2 student projects, or actually we will introduce a bit more a facility that we are now operating in LU Studio. And then we will end up with SED. And at the end, we will have a roundtable discussion of how each of us sees each other. It would be good if the students ask the questions to other students, and it's just us actually talking about amongst each other. So having said that, I leave the word to Elif.
Yes. So just to elaborate on that, so we want to discuss the meaning of simulation today, its role and its impact in design and research practices. And so we are representing here EmTech, led by Dr. Michael Weinstock, as you all know. And just to give a brief introduction about the types of work that we produce in EmTech, we have 3 main areas of research, and one of them is dynamic material systems and their fabrication, including robotic technologies. You will see an example of that. Another area of research, we focus on ecological urban design in emergent biomes. And another more recent area is immersive technologies, meaning the use of AR/VR technologies for participatory design and user feedback. And in a general sense, the way we approach computation and simulation is that we deal with many areas, including computational form finding, geometry rationalization, simulation of material behavior, as well as fabrication, assembly, including robotics. And so it involves many different scales and research areas, and we are very interested in the overlap of those research areas and scales. So having said that, I'd like to introduce our first team, and they will be presenting an MSc and MArch project that they've been developing for the past year and a half. And the focus was developing an AR/VR tool for participatory design. And you guys wanna come over? Thank you guys.
Good afternoon. We are Maria, Leana, Maria Cristina, and Carolina, who is absent today. And we're presenting our thesis project, which is Urban Glitch. So this project aims to examine a new approach in participatory design by using immersive technologies in an attempt to enhance the communication between the designer and the users while targeting the issue of unused public spaces in London. So participatory design usually involves all stakeholders in the design process pursuing a design outcome that better fits their needs. Participatory tools are workshops, surveys, and consultation, and usually take place either before or after the design stage. This research project aims to involve stakeholders in deeper design layers, introducing a new participatory design tool using immersive technologies. So, virtual reality creates an immersive experience where players are able to design within the platform in real time and also visualize and update their design outcome. Serious games are games with educational character, with an educational purpose, rather than pure entertainment. So introducing a serious game within a virtual reality environment helps in the enhancement of the motivation of the players, as it creates a playful and educational environment where players are assigned tasks. So this research project is structured in 3 stages. The first stage focuses on the development of the virtual reality platform and the expression of the people's opinion within it. The second stage focuses on a feedback loop where the design outcome is fed back to the virtual reality platform, and people are able to evaluate it and also redesign by altering certain parameters. The third stage is twofold, and it focuses on the one hand on the introduction of a multiplayer scenario where players interact with each other, and also on the other hand, it focuses on the creation of an adaptable space where stakeholders can express their opinion at any time. So the first step in creating the virtual reality platform was the creation of a visually consistent and realistic 3D environment of an experimental site. This site was of medium size. It demanded around 600 photographs in a consecutive shooting pattern. So the common points of these photographs, through a photogrammetry software, created a 3D point cloud that provided us with the mesh and the texture, the geometry and the texture of the mesh of the site. Due to its excessive number of polygons, we used the polygon reduction software, and finally, a 3D graphic software allowed us to reproject the original texture on the low polygon model in order to obtain a low resolution but high accuracy model. So after investigating public unused spaces in London, we were focused on New Era Estate, which is in Hoxton, and it houses around 350 people. The most interesting feature about the site is that it's a really close community, which is an asset for our purpose, as the people would be more invested in the redesign process of their public space. And aiming to gain a deeper understanding about the site efficiencies, we conducted an on-site survey where mainly residents, but also people who interact daily with the public space, express their opinion about certain major issues. The most important deficiency was the lack of communal activities due to lack of facilities, and most interviewees referred to lack of green areas, balconies, sport facilities, resting areas, which we classified in 4 categories: greenery, street furniture, building additions, and a customized one, in order to form the design program of our application.
The game itself was built as a 3D generator of spatial ideas that were built as simplified geometries. Its environment featured the realistic image of the site as it derived from the 3D scanning, And we aimed to create an accurate experience of the space that would bring together all the flaws and the problems that it would have. The building unit the players were given were a 50 by 50 by 50 centimeters cube, and they were able to create different assemblages as they wished. We also gave them the programmatic categories that you see that derived from the questionnaire that Maria Cristina mentioned earlier. While playing, the players also had a live information feature, which basically was a sort of an encoded expert that was meant to make them aware of some spatial features that do not necessarily come to mind to someone who's not expert in designing. So these features were the seatable area, the amount of shading, and the flow of people on the ground floor. And the visualizations of these information varied, as you're going to see in the video. Okay. So at first, you were just giving some information for yourself as a player, for us to keep some statistics. And then there was this introduction saying what the task of the game is and what you're required to do. You begin by selecting the category you're going to design for, but you're able to change at any minute. Then you're able to navigate through the site. You see the purple are common locations of this category, as I will explain later. You're also able to add some comments specifying exactly what you want something to be, because the cube was a very generic representation. This is the visualization of the seatable area, so everything that is in blue is supposed to be something you can sit on. And you see the black lines on the floor are the flow lines of the ground level, so you can see actively how you're changing them with the modules that you place. From the computational infrastructure of the game is based on the existence of an underlying 50 by 50 by 50 centimeters 3D grid that is invisible to the players. And basically, every time a player is adding a module on the site during runtime, the closest point of the grid is taking the value of 1. And this organization helped us achieve two major things. One of them is that we were able to run we gained an advantage of speed on the live calculations, because some of them would require significant computer speed, computer resources, and causing the game to lag and disrupt the flow of the players. And the second one is that with the scalar field that was deriving from this voting system, it was coupled with Emergent Cubes algorithm, and basically we were able to extract isosurface envelopes of preference. So we somehow got density maps, density definitions of voting for what people preferred and where. The first workshop was completed, and it counted 65 participants of various backgrounds and ages. And based on the game structure, the results that we were able to extract, the raw data that we were able to extract, featured the individual solutions of the players, so basically everything they designed, and the density definitions of their isosurface envelopes. But we also made some post-process analysis on those data based on distance from the grid points rather than yes or no, it's occupied or it's not, which enabled us to extract a more gradient density maps in 2D and 3D formats, as you're going to see. So this is sort of a visualization application. You're going to be able to see all this data. The first one are, as I said, the individual solutions of the players. So basically, you can slide through everything everyone designed. Then you're able to see the evolution of its program category, so like a growth pattern. Everything everyone designed according to program. The program hotspots, which as I said were based on if a grid point was occupied or not. They didn't exactly give the indicators of preference that we were hoping, and that's why we produced the analysis of the distance rather than this, which resulted in these more gradient isosurfaces. And then the heat maps that were basically horizontal slices on those isosurfaces that were indicating density not only as a boundary curve but also in area, in specific heights. And there was also a grouping of the players' comments, which enabled us to have a more refined idea of what they wanted to create through the cubes. So we released these data to architects in a design invitation that was shared through social media, and aiming to see how different designers were going to interpret this data into design proposals. And so we got 4 design proposals. We got 4 design proposals, and the next stage included of how we're gonna refeed this proposal into the game so that we would create a loop between the designers and architects and not just a linear interaction.
So the first goal of the phase 2 was identifying the designers' elements and translate them according to the game's language. So initially, we took each of these elements, for example, the lifts, the platforms, and arranged them according to the different design categories of the game, plus transforming their shape to this modular logic of the game. Once again, we ran a second experiment where the player is able to see this transformed geometry, and we gave them the specific parameters so that they can evaluate them. So if they picked one of the geometries, this panel appeared, and following a specific threshold that we gave them, they were able to scale the geometries, to move them in 3 different axes, to change the materiality in the form of 3 different opacities, as you can see. And the last bit is they can also add the comments and like or dislike other people's solutions. So with this experiment, we achieved the last stage towards validating our tool, which now in the architectural, now in the EmArch stage, we wanted to explore its potential to adapt space periodically according to the moving tenants' preferences, which in most of the cases in London or high-populated cities, in the context of social rented neighborhoods, they don't really find that the public or the private spaces respond to their needs. So we wanted to test this, seeking to design a collective proposal, which is derived from a private change that, thanks to the Urban Glitch tool, we were able to define using more than one people income. So basically, at this stage, we also wanted to explore a different manner of collaboration, of virtual collaboration, and that's why we proposed to use or to upgrade the platform to multiplayer. So in this experiment, we show how an individual is able to propose a private change and send it as an invitation to other players. So in this case, initially they send the description, which specifically is a building extension. And the invitees are able to accept this invitation, see other participants, such as the architects or owners or planners that don't really participate actively, but in a passive way so that they can follow the design process since an early stage. So within the virtual environment, the players are able to develop what's the initial proposal. And from this experiment, we obtained two main observations. The first one is that people tend to organize in design clusters, which can enhance participation in the way that people feel more confident on their skills to carry out this kind of activity, of design activity. And secondly, the outcome given them initially a proposal or a clearer goal, the design outcomes are better defined. So again, following our methodology, we analyzed the data from this experiment, and it gave us specific design drivers from which we were able to inform our design. For example, we observed that it was highly evaluated a permeable non-structural element, a care for side overlooking, or the potential to extend the proposal to the upper levels. So with this, sorry, it's not showing. Well, I will skip to the final design. With this design, we proposed a combination of heavyweight and lightweight elements that act in a very adaptable manner that, when coupled with the tool, shows the real potential of the method of developing, when used more times by different tenants, can generate a different architectural outcome.
So, seeing back now, we come to the conclusion that using the virtual reality in participatory design specifically, there is the possibility to create this middle ground between the designers and the users, because they both come from a different point of view regarding space. The designers have this expert opinion and they use this abstracted way of designing, whereas the users, they have the personal experience with the space that is coming from many years of living there. So we believe that through virtual reality, there is a way of bridging their gaps in their perceptual and conceptual thresholds by creating this dynamic ground where they're able to exchange ideas and reach a common solution.
Regarding user-user interaction, this virtual test, we explore different collaboration techniques that at the latest stage, we confirm that the multiplayer is the best approach towards obtaining this group thinking that help us developing a better form design and enhanced participation.
So applying the game mentality and introducing tasks and an incentive to the virtual reality game enhanced the players' motivation, which led to a more effective participation in the design process. So also virtual reality helped in the better understanding of the scale and the actual design of untrained players. So combining immersive technologies and serious games enhance the communication between the players, as the girls have already said, in a collective activity, but also between the players and the architect in a more informative process. Thank you.
Yeah, I would like to speak about the thesis project, which was developed recently in Emergent Technologies and Design Studio. And it's a teamwork with my teammate Mithuna, who is unfortunately not here today. And I'm going to talk about the value of digital simulations and computational design in this project, and how we actually combined together and brought everything into one integrated system. So let me briefly introduce our design ambition and aim. Basically, looking at current Arctic scenarios and trends, we realized that there is the predicted population influx due to local and global factors. The local factor is the moving away from the coastline due to coastal erosion, and the global trend is happening because of the global warming and more availability of potential resources. Therefore, we looked into this as the opportunity to create an integrated fabrication system in order to mitigate this potential population influx. And we also observed an interesting phenomena, which is called thermokarst lakes, which are appearing due to permafrost thawing, where there is a lot of abundance of peat on the late stages of lake development. And we wanted to use this potential abundance of resources as our main material in order to utilize it and use it locally. Therefore, our research question was, how can locally sourced peat material be utilized to create an efficient fabrication system that responds to changing Arctic environment in the near future? And the main challenge we faced in the project was the highly interconnected data from environmental factors, from material experiments we conducted, and also from fabrication system which we decided to go for. The fabrication system we selected was the robotic fabrication due to challenges of constructions which are currently presented in the Arctic, such as dangerous construction and lack of human labor. So we decided to go for a complete housing settlement, which will be adopted to this environmental and social criteria. So we started from development. So we started from development of the primitive, which was basically the translation of the social needs of people in this area into one housing unit, which is basically the connection of dome-like shapes, because dome shapes are structurally stable and they have extensive presence in Arctic construction. On a global scale, we conducted a genetic algorithm which was incorporating both environmental, material, and fabrication criteria. The environmental criteria we used were maximization of solar exposure and minimization of wind exposure. The fabricational criteria derived from the robotic reach of the selected robot, as well as from the fact that all our structures must be compression only, so the placement is only from outside. Therefore, we decided that our criteria would be the minimization of robotic tracks length. And the material criteria was the actual minimization of material usage, which can also potentially lead to minimization of time of construction. And all of these criteria are accompanied with parameters, which are basically a set of actions which can happen with the primitive units within the settlement. So these are kind of set of rules in which compound units are connected or not connected between each other. We selected a set of genes or a set of actions which can happen to the primitive, and they happen both on global and local scale, such as change of proportion between body parts within one housing unit, rotation of the whole unit, or moving of the units between each other. Also, we implemented 2 rules in order to fulfill the criteria of robotic reach and adjust the robotic morphospace. If units are too close to each other and the compound house is not reachable by the robot, they have the possibility to move away from each other or rotate away from each other. Therefore, by implementing this simulation, we were able to see the impact of different clustering scenarios, such as completely compound scenario in which houses are all interconnected between each other in a maximum amount of primitive units within one house. What we observed that even this type of clustering is highly efficient for wind exposure and tool path length. It's completely inefficient for solar exposure due to a minimum of exposed area of the house. The dispersed settlement was actually the opposite scenario. Due to the fact that houses were completely detached from each other, it was inefficient for wind exposure. Therefore, the intermediate settlement clustering system was selected as a balanced solution between all the criteria. What was important to mention in this kind of simulation is that the scale of simulation was really important, and the abstraction of data was important as well. We couldn't implement on the environmental criteria within one simulation, so we needed to choose carefully. The second set of experiments was conducted in order to determine the thermal performance of the house, which was really important to understand due to harsh environmental conditions in the Arctic. The temperature can span from -10 to -30 degrees in a cold winter month. Therefore, we conducted several experiments working both in section or in 3D model of the house. What is important to mention is that due to a high complexity of thermal performance and data input for the simulation, the actual house we observed was really simplified in order to understand the result better. So in the first experiment, we observed the impact of the base to the house, which actually increased the thermal performance and decreased the heat loss in a transitional space between house and unit and the ground up to 40%. Due to this low solar gain, the actual sun heating was inefficient. Therefore, we proposed underflow heating for the whole house. As you can see from the diagrams, underflow heating provided us the uniform thermal performance within the house and efficient thermal comfort, even in a cold winter month. After the global experiment, we abstracted one house to be explored in detail. What we understood is that global experiment doesn't really give us a structurally stable shape, so we needed to optimize it, and we selected force-driven form finding as a way to create a structurally stable system, which is also compression only. It was important for our material and our environment. And the inputs for this experiment were the outline of the shell from programmatic distribution, the height differentiation, and the height limit due to a high wind load. And basically the shape is created by manipulating the force flow equilibrium, as you can see from the video. And the morphology of the shell is changing simultaneously, giving us the outcome, the design outcome, which we are aiming to achieve. As a conclusion of this experiment, we can admit that force-driven form finding was an efficient tool to create structurally stable compression-only systems. However, high differentiation within the dome shape creates high forces within the valleys, which means that the more differentiation we want, the more forces we are getting within the structure. In regards to the tessellation, the customized cutting pattern was developed through abstraction of different data sets from structural analysis. Therefore, the horizontal cutting lines are actually isocurves which are moved down in the areas of the biggest utilization and moved up in the areas of smallest utilization. Therefore, the efficient interlocking is created. The vertical cutting lines are abstracted out of physical force lines with customized density. Also, we developed our custom tool for planarization of the panels because it was important for our material to have flat panels only. It was not possible to produce doubly curved panels. However, our shell was doubly curved. So we developed a two-step process, and the second step, which you can see on the video, it was the customized planarization algorithm, which basically fulfilled two criteria. It was moving points of each panel towards coplanarity without disturbing the continuity of a surface. As a result of this experiment, we can admit that customized tessellation brings a lot of complexity into the cutting pattern, because each panel is in the end different. And the planarization algorithm, although it worked efficiently, it brought distortion to the panels again. And finally, we needed to use some simulations in order to simulate something which you can't really simulate physically, which is robotic pick and place. And through the experiment, we could actually track the amount of rotations within the robot and the amount of angles which the panel needs to be rotated within. And we could maximize it or minimize it accordingly to our needs. Therefore, we tested 3 different interlocking patterns within the robotic system. And the last robotic pattern actually integrated the main feature of robotic pick and place, such as no friction while panel is placed, and sufficient friction when panel is staying within its place. So what we realized is that we need two different criteria and 2 different methods in order to create horizontal and vertical interlocking. So for horizontal interlocking, we introduced a tapering, and for vertical interlocking, we introduced inclined plane, which is inclined against the direction of panel's collapse. What was also important is the implementation of these simulations within the customized tool for the robotic pick and place. And through different iterations, we created an end effector out of gripper and connection point to the robot, which was basically able to fulfill our criteria to increase the grip in order to pick the panels efficiently, but also not to increase the length of the whole system in order to prevent singularities and increasage of additional rotations. Therefore, the simulation itself helped us a lot to actually derive the toolpath of the robot. The toolpath itself is the sequential robotic move from one oriented plane to another oriented plane, and from opened gripper position to closed gripper position. It's worth to mention that due to previously mentioned custom tessellation pattern, each panel shape was different, and even within one panel, each angle is different. Therefore, highly expensive computation within this simulation was actually really important. In terms of global assembly, we used increment analysis, which you can see on the right, in order to derive our assembly sequence. So the assembly itself consists of sequential placement of self-sufficient dome-like shapes, and the last part is the cup, which is placed, assembled on the ground, then secured by the cable and placed the last. Therefore, the sequential combination of the simulations on global and local scale helped us to translate different environmental and fabricational data within actual design proposal. Also, it helped us to evaluate our fabrication system in order to understand its place within the within existing robotic fabrication systems. What we realized is that the rate of our system, the speed of our system, is much more, almost 3 times more than speed of human labor. However, it's more or less on the same level with the existing fabrication systems. As a conclusion, I can admit that architectural simulations helped us a lot to bring together these different data into one integrated system. And genetic algorithm for us was helpful on a global scale. It was helpful to determine topological relationships within the settlement, whereas robotic simulations and force-driven form finding help us to understand the structural performance of one compound house. Therefore, this sequence from global to local, in our opinion, is necessary for efficient fabrication system design. Speaking about limitations, we can admit that these types of simulations with environmental and fabrication data, they are really computationally expensive, and they require a lot of time to proceed. Scale of simulation is important as well. The simulation should be conducted within one scale. And moreover, digital experiments should always be followed by physical experiments in order to prevent further errors and actually prove the concept. Thank you.
We'll move now to the landscape urbanism bit of the afternoon. What we are going to see is one just finished project, an Emergent project that is dealing with some form of digital simulation of sand dunes. And the second project is not going to be one student project, but more of an introduction of a facility that we've just opened in near the LU studio. That is a facility which will be open for any student about physical simulations. So Rimjim will actually follow on a bit on her presentation, talking a bit of how she has dealt as well with reverse modeling, and then I will chip in to introduce this facility, this sort of physical modeling, and then we will show some sort of like first results that we have obtained over the last couple of weeks, because this facility was open only just right before Christmas. So I'll leave it to Rimjim to introduce her project.
Hello, good afternoon, everyone. I'm Rimjim Chauhan, and I'm about to discuss one of the projects that we did this past year, which was done by a team of 3 people, Majide Sayedi, Taosun, and me included. It was a project about Canary Islands. I'm pretty sure a lot of you have heard about them. They're a set of Spanish islands in the Atlantic Ocean, and they're really popular nowadays as a tourist destination. And it's because of their amazing sunny weather, a lot of their beautiful landscapes, and but what we don't know about it is that there's a lot of land abandonment in the area, and a lot of issues, spatial issues, a lot of economic issues that are rooted within all the islands in the archipelago. And the abandonment is the agricultural abandonment. It's even more alarming when you consider that it just 60 years ago, all of their economy was based on agriculture and fisheries. The question dealt in this project was how does a territory which was so deeply rooted and connected with their land get so disconnected with it? So we had a visit last spring to Canary Islands, and spoiler alert, it's tourism. Now, don't get me wrong, tourism is very important in Canary Islands. In fact, back in the 60s, the islands had experienced a huge economic boost due to the infrastructural development of the islands for tourism. But it also led to better trade relations in all of the European Union, but it also led to more food imports, which meant that the local production suffered, and it led to abandonment all over the islands towards the primary sector. And now, in our site visit and interviews, we found that there was one island in particular that this was really rampant in, which is island of Lanzarote. Now, it has a diverse range of agricultural landscapes, like the Lajeria vine landscape and the Paso de la Hable sandscape, which you can see in this box here. It's a corridor in which sand moves across the island from the beaches, so it's marine sand moving across with just wind. So it's a really pretty corridor of just sand in the middle of black volcanic soils, and it has this very peculiar variation of sand depth, in which there are locally known regions of varying sand depths, which are important because those different sand depths mean that there are a different variety of crops that can be grown in each depth. So for example, in the red bands, as you see, fleshy fruits such as melons, watermelons, zucchinis can be grown, and in the yellow parts there are potatoes and other sturdier crops. So it looks a bit like this. It's really flat, not like sand dunes or anything, sand sheets, and it's really pretty, but a lot of it is abandoned. So it suffers ecologically as well as in terms of tourist visitation as well, because there's nothing to see there. The part that our simulations and our analysis talked about was how this sand circulates. So because it is such a complex phenomenon that happens here, it deals with sand rotation and how the crops themselves need to get rotated per season. So, but all this, the landscape, the beauty of the landscape lies in this complexity. So we had to take a look at all the factors of where these sand depths take place, where the crop rotation takes place, and what the sand rotation actually looks like into consideration. And with that, we came to simulating what these aeolian processes would be. So we used a lot of softwares for wind as well as sand simulations. For wind, we primarily used softwares for both kinds. The softwares that the simulations work on, they work on a system called cellular automata, which I'm sure a lot of us are familiar with already. And So cellular automata works on the fact that there is a grid of cells, and whatever happens in one cell gets replicated in the other cells as per an iteration that takes place. And with this, we can take sort of simulations of fluvial or aeolian systems. So the sediments were like each cell in the grid of a particular landscape that we take passes on the effect to the other cells as well. It works in sand and wind simulations in a similar manner, and the simulations that we worked on various scales of operation. So if this is like a close-up of the corridor of sand, we had several simulations working on whether we're working on the macro scale or the micro scale. So our wind simulations, which we did in ArcGIS, airflow analyst and as well as Autodesk flow design. They worked on getting an idea of the slope in the terrain, because it's not a very terraneous site. It's really gradual slope. But since the deposition takes place as a result of sand saltation, it leads to very interesting sort of spectrum of velocity and depth. And it led to the diagram that we had seen before, where we had the red-green bands. So we'd extracted it from the simulations and got a velocity and depth spectrum, which led us to demarcate the areas where we could grow particular crops or have certain infrastructures. So, and the sand simulations, we worked with a Python script which simulates sand as per the Werner model of sand dunes. And so what we'd done was that each crop, because it's grown in sand, it has a different variation of the planting frame than we would see normally. So we put these frames in simulations, and we had a catalog of the sand channeling that takes place through these interventions. And on the macro scale, they lead to very interesting formations of dunes and sand mounds in longitudinal variations. And so these are some of the ones that we had in particular had an experimentation with. So if you see that we have extracted some of the medial axis as well, and we tried to demarcate where the accumulation of sands are. And then we tried to do it as per the grid plantation frame as well. And all of this was a step towards demarcating it on a macro territorial basis, where we were dividing those green and those red bands that we saw previously into different areas, where where each segment was allotted to different crops, and it led to a gradual formation of a sandscape, which we will see further as well. So at the northeasternmost edge of the site, we had pumpkins, and you can see some of the labor dynamics that we had researched into as well. And so the next step was, as we know that in cellular automata, when we simulate certain things, there is a sand shadow that forms while we're simulating. So in the sand shadow, the next band of crops was planned, which need low sand depth, such as zucchini. And then we get the second sand band of melons, and then we move on to watermelons. So this led to a sort of cyclic rotation, well, I wouldn't call it rotation, but that's the easiest way to describe it, of sands, such as seen in this diagram as well. And we had certain breaks in these bands, so as to make the sizes of the fields a bit more manageable as well. And this works on the same principle as a memory cache would work, that it has a more easier access for the farmers that have fields right next to them. Then because the sand is a resource that enables them to cultivate. Because of the sand, they don't have to irrigate their fields, because it acts as a layer of protection of the moisture. So in certain areas, we had these sand caches where the sand would flow more freely and be more accessible to the fields that were downwind of the sand flow. And then we see how we put different seasonality of crop rotations as per the prevailing wind direction of that season. And it all takes place at a stretch of 3 years. And then we arrive at this sort of sandscape, which generated itself with a process that was taken out of simulation. So each step comes after the other because it is a result of the previous band of sandscape that we came. So with this choreography and a system of crop and sand rotation, sandscape which is generated, and it also has a system of infrastructure such as storages, accommodations, and farm stays, which we integrated within the generation of the landscape. Now, the quantitative data would obviously come from the labor dynamics, but when we define it qualitatively, we had another set of more detailed simulations that we took on the micro-territorial level. So this is an area right over here, this area. It's an area between one of the red bands and one of the yellow bands, and it was chosen to be a farm stay for the tourists to come and interact and be part of the agricultural landscape. And for this, what we did was we had simulations with tall obstacles north of the site, and they formed a sort of 2 to 3 meters of mounds. And you can see the simulation, the basic simulation that we had, and we extracted the medial axis from, and then we extrapolated certain grids that were used in the planning of the plantation as well. And then what we did was we took these medial axis, and then we chose certain grids to have placement of obstacles so that we can see how the sand accumulation on a smaller scale is affected as well. And that led to a certain catalog of different typologies of architectural morphologies that we could come up with. And as you can see in this, we have taken 3 iterations of that simulation, and we've worked out how the transition of the dune takes place across the micro landscape. So you can see in the diagram how like certain built forms can be built out of these geometries that we get from those obstacles as well. And so this is an animation of how the dune moves through this. And these walls are also placed in certain stages so that the sand, when it gets manipulated, for example, when we did like 3 iterations after that, we installed another wall so that the sand, we can see how it moves with the wall as well. And so we come up with this sort of architectural and design morphology that arises from the simulations themselves. And then this, when we work it up to the larger scale of the whole sandscape, we can see how the sand, the produce, and the labors, they come back into this whole socioeconomic and landscape linkage, this relationship, which works on the larger scale of the whole what we call agroproductive sandscape. And these little mechanisms of the sand moving from one place to another also go into this diagram of flow of the people as well as the sand as a resource. Then this simulation then we replicated as to how it would work in a certain projective scenario. For example, if when we take this module as a prototype to in the whole corridor of sand and place it, we have certain areas where it would be viable, and according to the circumstances, like social circumstances and the physical geomorphological attributes of that area, they can be adapted to the similar design principles and policies and replicated over the landscape in certain different phases. And this would link, this would make the tourism as this would make this place more lively, and the tourism can start interacting with the area, and also result in an inflow of people in this area and make it more economically productive and ecologically more balanced, because the sandscape is something that was formed from the agroproductive dynamics that happened traditionally. Now, with this, we also have certain other simulations that we usually do in AALU, which are more of fluvial simulations, which are done with river and water systems. And it uses certain different softwares than the ones we've discussed right now. It uses Caesar, and it uses certain ArcGIS input as well. So as we know, like there are certain different typologies of rivers that arises from the geomorphology of the terrain as well as the amount of water that the area receives. So these different variations and classifications, they have a certain method of how these come out to be. For example, a meandering river works by having one channel which winds its way across a terrain and creates a flood plain, and it deposits sediments on the insides of the curves, leading to point bar deposits, and erodes the outside of the banks, which leads to a wider flood basin. And we usually use Caesar as a software for this. Caesar is another software that works on the cellular automaton model, and it has certain variations that can be done in the parameters. For example, you can use the catchment mode, which is for rainfall data, or you can use the reach mode, which is basically the water that gets input into the stream itself. For example, this is a simulation, example of a simulation that works in Caesar. So in this, you can see how a traditional meandering river can have a much more potential for more meandering, and across the whole timeline, this was around 5,000 days worth of projected simulations. It didn't actually take 5,000 days, and it gives a lot of results in terms of the topography, what the flow velocity would be, what the erosion and sedimentation would be. And you can take this into other certain modeling softwares and make certain analysis through the outputs that you get. For example, here we can see how the avulsions in the river take place, and you can measure the diameter of the curvature of the river. Here's an example of the river depths and the flow velocity and the certain shift in the channel of the major channel of the river as well. And like through all these simulations, you can see how we can visualize certain known geomorphologies of rivers. And like another thing that we did like during this one of these projects was how we can intervene in them. So another thing you can do in Caesar is you can intervene and put barriers or create channels, and then you can put them in the middle of the simulations, and you can have it as an input, and then with the output you do certain more changes, then you run another simulation on it, and then you can see how if you're trying to accelerate the river, or if you're widening the channel, what repercussions that would have on the landscape. It's an easy visualization to have. Now, when we work on Caesar and CEM models, it's easier for larger landscapes which have a lot of complexities, and you can visualize that digitally. But for smaller simulations in which you just want to see how the curvature of the river works, or how a certain meander takes place, or how an oxbow is formed, it's better to do certain small-scale physical simulations. And for that, I'll hand over to Eduardo.
Just as a quick note, we forgot to mention that the sun simulations that we've seen before, they were brought initially like 3 years ago from University of Southampton. We had a scholar that actually gave us access to the code, and the Caesar, the bit that you've seen from the river, comes from BGS, the British Geological Survey, and we actually have somebody from BGS every year sort of like giving an intro of how to use it's a proprietary kind of like closed software. So what we are going to see now is we've just recently opened a We've built small-scale physical simulation of river and sort of like aquatic systems in the LU studio. This is part of a longer-term research that we've carried before of how can we approach the different morphologies of the landscape and how models that explain how the landscape changes, both digitally, as you've seen, and physically. So physically, we can actually get hold of some models that explain, for example, how meanders, braided systems, dejection cones work in terms of river, estuaries, tidal creeks, and longshore drift, perhaps, but definitely sandbars and tidal creeks we can simulate physically with models, which are physical models, which are small-scale version of reality. We can then move into Gilbert deltas, which is only one type of deltas. Digital deltas are a bit difficult to do. You can also do dunes, although physically with physical simulations with dunes is a bit tricky. You can get the entire studio full of sand if you don't organize properly. Glaciers are a bit tricky as well, but you can do something, glaciers. And karst. Physical simulations typically work on the principle of similitude, in that if you get materials small, they do behave similarly to the large scale. However, there are principles of dynamic measurement that start to sort of like fail if you come down too much. For example, in terms of water systems, you can scale down a process 30 times and still measure stuff and it be accurate. Sediments, for example, as we'll see, it ends up being a bit more, I would say, qualitative and not so much quantitative, yet still works for certain actions. No? The idea or the difficulty is being able to capture the data, and you'll see that a lot of the effort is how do you get from the sort of like material stuff that is there and you bring it back into the computer. That's the bit that is in LU Studio. The idea is that it's shared facility, so if anybody wants to use it over the year, just give us a ring and we can see how can we share, because the students will not be using in LU all the time this facility, and the idea is that this is one of other facilities that we can build over the years in the AA that try to bring in this sort of like physical approach to modeling and data capturing, and that can be followed by either wind simulation or sort of like wind tunnels and so on and so forth. But that is already there. It's just as you get into the LU Studio a bit on the left, no? And it's a physical, well, you'll see later how it works, and Jimmy will show you what we've done so far, which is a couple of weeks work of how we've been trying to capture data.
Hello.
5 minutes or 3 or 4 minutes.
Yep. Okay. So pretty much with this physical simulation tank, it's really just trying to understand the relationship between the water and the sediments that we use. So looking at how much water we use in ratio with the sand, we have to understand like the constraints and attributes that goes along with them. Looking at the tank itself, you would need an outlet and an inlet, understanding like how it's being captured physically, but then also trying to see how we capture this physical model into a digital format. So we having to have it digitally, we start to then transform it in the form of artificial intelligent way of capturing this model and trying to understand these physicalities that we can understand further along the way.
Just chipping in, we use real-time data capturing using color-coded water tainted. We want to use in the future training data, basically using photogrammetry to fabricate a 3D, which helps smoothen by using, let's hope we can use machine learning to clean up the real capture data. So that's something we just only started to sketch, and Claudio, who's not around here, will be in charge of it, hopefully.
And so here's just a quick video of what we were experimenting with these simulations. The one on the left right here, it's really trying to see the relationship between the slope, but also the sediments and water. As we have the slope, and we naturally get a straight line, but also creating a delta in this situation. This was a lapse of 4 hours. In this case right here, we were trying to accelerate this process, but with the slope of pretty much almost to a flat level, but not really getting too many results in this case, due to the fact that we now have a better understanding of the sediment properties, but also the water flow rate as well. So we understand that more as well. So this one right here is more of an example of like a next result of the model. This is what we've created based on introducing pools and trying to understand different type of different forms with the sand and in relation to the water. This one right here is just trying to simulate the digital model, but introducing it to capture it through artificial intelligence, and just trying to understand how we could capture the physical model, but really just trying to have the computer to like to capture it in live real time. Yeah. This one right here as well. And so this is the last result of the model of simulating the tank with pools and meandering effects of the sand with the water.
How many hours was this? Like
so this one was this is a 4.5 hour run. So yeah, that's this one. Yeah.
Are you recording? Yeah, alright, recording.
Oh, sorry, there is noise and we didn't want the noise.
Are you recording? Yeah, alright, recording.
The idea is that in the future we want to go to, oh sorry, with the mouse. Yeah, situations like this where we can really play the model on the one side and a digital version that runs live on the other side, evaluating its performance, the areas, the amount of pools, the ecology that it's taking. That's an exhibition we worked upon like 3 or 4 years ago, where it was been doing that. But that was a live model calculating and evaluating the physical, So yeah, that's the sort of like bit that we've done over the last 2 weeks. And by all means, we invite everybody that is curious about it or thinks can be applicable to the projects to come and ask. Okay. Good.
So for SED, we will be presenting 2 projects. And through this project, we will want to illustrate, one, the role of simulation in our program, and also that differentiation between the MSc and the MR, something that comes up in many discussions and many visits of the external examiners. Can you hear me like this, or shall I go? So that the differentiation that we provide as an explanation of the difference between the MSc and the MARC is that the MSc is research that is done in SED, it is done individually, that allows the student to determine the area of design applicability of that research. And the design applicability may be regional, within the country, different climatic zones and so forth, or different building types, the products of the research being applicable to different building types. Whereas with the MR, the student selects a site somewhere, usually in their home context, and that site becomes the place for a design project. The design project is an embodiment of the research that the student has done for the MR. Now, simulation is really an extremely interesting thing. It can be very, very abstract as a process, yet lead to very specific results, or vice versa. It may appear to be very specific and then lead to results that are very abstract. And in there lies both the excitement intellectually and physically and practically, and also the risks. Because there are very great risks that if we're not able to interpret correctly, or if we don't understand the principles behind the software, great errors can take place. Now, on the SED program, what we study buildings and we study outdoor spaces and the relationship between the two. And we look at them environmentally through the laws of physics as they are embodied in computer software primarily. And what becomes really critical is the notion of performance. We want to be able to know something about the results, so that the results are not just anything, they are an indication of performance, a performance that can be compared with something else, a target, a benchmark, and so forth. Now, why should we believe the results of simulation, of any simulation? Is a very good question, and I think it was already mentioned by one of the presenters. We shouldn't necessarily believe, unless we have some indication that we should believe at least a little. And so what we do for this is to take measurements. We take measurements in real buildings, and then we try to calibrate our computer software with these measurements. And of course, we don't necessarily need to do it in great precision each time, because once we have done it properly and we start believing that, yes, indeed, we can trust simulation to give us meaningful, realistic, credible results that we can use for design, and also for comparing our building with such standards, benchmarks, and so forth. So here you see, for example, certain measurements have been taken, spot measurements with instruments that register the temperature, and then simulation results are compared with temperature readings taken by a data logger over a period of a week or so. And do we expect to find complete agreement? No. But how much this agreement should be acceptable? Well, it's an open question, and experience is needed to tell us. Here I can tell you that the agreement is reasonable. The green is, I think, let's see. The green is the simulation, and the blue is the recording of the temperatures. And in fact, one can go into the question of by how much they are in disagreement and what that means. But I won't do that now. Having obtained a meaningful agreement, then we can proceed in running simulations where we change the values of parameters in order to move towards certain results that interest us, and results which confirm our design or which make us want to change it. And so over the years, performance in terms of environmental design has been measured by a number of different metrics. One important metric has been energy, in the sense that this is a resource that's non-renewable in the way in which it is used now, and so we measure it, and being able to reduce its use then becomes a positive achievement. But as over the years we have been able to reduce the energy used in buildings quite dramatically, now building satisfaction of occupants, comfort within the buildings and outside the buildings become another metric. And so now we will proceed with these presentations. First, MSc project, and then an MArch project, which have been undertaken and completed recently in SED.
Good afternoon. My name is Chiara Multari. I completed my MSc in Sustainable Environmental Design this year, so in September 2017. And my MSc dissertation focused on office buildings, so on commercial offices in London. And the choice verted on office buildings because the scale of the problem obviously is quite large. It focused on architectural features and passive design strategies aimed at achieving energy savings and occupants' comfort. So simulation tools were extremely important for the development of this research because its aim was to produce guidelines for future designs based on measurable values and proven results. So, as I said, as I mentioned, the reason why I chose office buildings is that workplaces are extremely complex environments, and there is a huge potential with this kind of analysis and simulations to achieve, to improve their design, their energy performance, and in general, the occupants' satisfaction. So, my pre-research analysis highlighted that contemporary workspaces are characterized by extremely high internal loads due mainly related to three main factors. So the high occupancy, the office equipment, and the interior lighting. As for the occupancy, current trends are moving toward a more intense use of space, which means high design densities, especially related to modern sharing models such as co-working or desking, which obviously rise the number of people per square meter, and also the real occupancy is rising. Related to the topic of occupancy is there is the theme of a rising demand for technology, because modern offices are characterized by a huge amount of IT devices, which obviously produce a huge amount of heat, and finally the interior lighting. So the simulation tools that we used, that we learned during our program, so in SED, were used basically to conduct daylight analysis and thermal analysis. The simulation were useful to test the different design strategies of different measures to improve the daylight and the thermal performance, and also to test to discover which measures are the most effective. For daylight analysis, we used the plugins for Rhino, Grasshopper, and Ladybug, whereas for thermal analysis, we were using the OpenStudio interface, which is a more user-friendly software for the Energy Plus engine. The outcome of this research helped me optimize a prototype building design and a number of adjustable variants that can serve different site conditions and design brief. The first cycle of simulation were run on a basic showbox model, which is the one that you can see on your right, sorry, on your left. And was a very basic model in order to test the impact of different parameters. This model was further developed in a more complex atrium building, which embodied basically all the knowledge that we gained during the SED program. So the architectural features were already chosen in order to achieve very good performance, both in terms of daylight and thermal performance. And I mean, some data, but are quite technical, so are shown. This is not a very technical presentation because it would have been very boring. So the first simulation that I conducted were related to daylight performance, and the first cycle of simulation was performed in an obstructed condition. As a second step, I tested the impact of more realistic conditions, so the urban context and obstruction. And finally, I test the impact of the shading, which can be very useful even in cold climates like the one of London. So This is a typical daylight simulation. This is showing the daylight factor, and as I said at the beginning, the first cycles of simulation were run on a very basic showbox model. So as you can see, the daylight factor is consistently impacted by the urban context. So a typical third floor unit, which is the unobstructed condition, is is showing a 5% daylight factor, whereas a typical first floor unit is receiving almost half the daylight, as the mean daylight factor is around 2.5. This section are summarizing the results of the daylight simulation, and thanks to this section I mapped the depth of passive zone. We can define the passive zone as the area of a floor plate that receive enough daylight, like satisfying levels of daylight to be throughout the year, to be almost independent from artificial lighting. And as you can see, the depth of the passive zone is always reduced by the impact of different factors. And one of these factors is obviously the obstruction. So other cycles of daylight simulation were run to optimize the performance on southern orientation, and for this reason, overhangs like shading devices were tested. The impact of shading devices to contrast over-illumination and glare problems were tested, whereas other simulation regarded the typical daylight devices, such as light shelves, internal, external, or external only, which helps, generally speaking, to better distribute the light throughout the depth of the room. As you can see, it's quite important to evaluate also the different sky conditions when considering daylight, because in a typical sunny day in mid-season, the area close to the window on the southern orientation is showing clearly over-illumination problems. And for this reason, shading devices can be very helpful. Obviously, it also is very useful taking into account that huge amount of hours during a year are characterized by overcast condition in this climate. So a balance needs to be achieved. The second part of my studies related to thermal performance, and as you can see, from the info boxes, all the values regarding internal loads and design density were set quite high in order to test the building under stress condition. The prototype building that I developed is an atrium building, so it's quite different from the typical layout of commercial offices, which usually have the cores and services in a central position. Basically, with my dissertation, I wanted to discover and to explore the potential of an atrium in improving the thermal performance of a building. So what I did was to study very successful precedents, which relocated the function of meeting space and cores and facilities from the central area to peripheral area. in the case of my building, I relocated these functions toward a west orientation, which is usually the less suitable for working activities, as it is the most difficult to shield, to protect, and the daylight conditions are usually the less favorable. So these are some of the tests of the measures that in the end resulted to be the most efficient in improving the thermal performance of the building. So I tested the impact of natural ventilation in reducing the cooling loads, the shading of the glazed atrium, as I mentioned before, overhangs and light shelves, based on the analysis that I previously conducted for daylight performance. And in the end, I explored the potential of using the atrium to cross-ventilate the building. So yeah, different ventilation strategies were used were tested for different periods of the year. And results were quite impressive because starting from a base case of a typical mechanical ventilation-only building, although we are already talking about of a very well-performing building, because, as I mentioned, its features were had already been optimized thanks to the knowledge that I gained during the year. I achieved 88%, so almost 90% reduction in cooling loads, which is quite impressive, and the heating loads by recirculating the area, the air, the preheated air in the atrium helped me achieve a 20% reduction of heating loads. So the results of this research were finally embodied in planning proposals, schematic planning proposals for design applicability, and obviously these schematics can serve for future designs as general principles. So the first step was organizing the functions in a clever way according to the results of the research. The passive zones were overlaid on the floor plates, and different adjustments were made to optimize or to maximize the benefit of placing the workstation in the areas with good daylight availability. And finally, all the results of the research were embodied in this planning proposal. So the areas of the floor plate which were suffering from poor daylight were devoted to activities like support activities or circulation spaces, whereas all the workstation, fixed, shared hotspot desks were placed in the areas where daylight is quite consistent. So these are different proposals. Basically, the atrium is always present in the schematics that I developed, as it was proven to be a very effective and a very successful feature for an office buildings, whereas facilities and cores and meeting spaces were relocated in different orientation to explore different design possibilities. So in the end, I mean, simulation tools in this case were extremely useful to develop better designs and to help measure which I mean the achievement in terms of energy efficiency that we can have. Sorry, I was a little bit unprepared to the conclusion phase. Thank you.
Good afternoon, everyone. My name is Rafael, and I'm going to show you a bit of the outcome of my research. I did an EMARC last year, and this was my dissertation project. In SED, we use the simulation tools for mainly, like, I would say, on two levels. One would be to assess the physical conditions that buildings are providing to the occupants and to improve them. And when they are not met, then to quantify the energy needed on these buildings to provide these conditions. So what I'm going to show you is the design application that was conducted here in London. It relates to Chiara's research. It's an office building in London also, which is located in that red tiny bit on the corner next to Old Street. We are there at the AA. So, all throughout the design process, we use simulation tools to identify the design constraints and potentials and how to use them to provide a better environment for the users. This was the site for the office building. As you can see, it's a rectangular site, roughly 25 by 70 meters, with a tiny peak on the corner. It's located in a very narrow environment. The streets on the east and west are roughly 6 meters wide, and the ones on north and south are a bit wider, like 10, 15 meters. Currently, the site is occupied by a car park that is 1 story below street level, which provides the cars with a very nice sunny environment. So this is what we have at the moment, a very constrained site. As you can see on the sections on the top, it gets very, very narrow on the east and west side, and a bit better on south and north. To design a sustainable building in such an environment requires to analyze the actual site precisely to see what are the constraints and the potential that we can use. Such a dense urban environment is mainly problematic for daylight. You can imagine, and as we have seen now, how the building so close to our building constrain daylight and then solar access. So the first thing that I did was a solar simulation during winter to identify what is the areas of a potential boxy building would enjoy with sunlight. Only the south facade enjoys a bit of sun and the roof, which is not very useful. Then that potential boxy building, if we analyze daylight access, we start seeing patterns that we can use for a later design stage. We can see how the corners enjoy much better daylight and how the central part of the whole plot is very obstructed with barely nothing reaching the interior space. All these results are used as a starting point to start thinking what would be the footprint and the layout of the building. So the first design decision was to introduce a ramp and the entrance of the building on the top peak corner that would lead to a semi-public underground space. That would be used for co-working spaces or for other public activities, on top of which the first floor would be located. The first floor, as we have seen, has a very restrained daylight availability, and the footprint of the building was designed according to this situation. The two curves were excavated on the massing to create two outdoor spaces on both sides that enjoy solar access on key moments of the year, and also reduce and optimize, in a way, the daylight inside our potential floor plate. From there, the final massing was defined with an architectural reasons, and taking into account the potential solar access that we could have. So instead of having only one facade to south, we'll have two. The volume on the north is slightly higher, it's 2 floors, while the one on the south is 1. And that allows to have a sunny terrace on top for the people working in the office to have a break and to enjoy during winter or the mild seasons, or even summer. So back to our lower floor plate. This is the first floor, and this was used as an initial step on how to lay out and how to organize the floor plate. It's quite obvious that only a small part of the building has an adequate daylight, and there's a very deep plan happening all the way here. So it became quite straightforward that the building would need an atrium or 2 atriums, one on each side. There is a problem with atriums and office buildings and developers in central London. Every square meter of atrium that you have is a square meter that you cannot rent or that you cannot sell. So nobody likes them. We people from SED, we like them because they are very useful for daylight and for ventilation. So in order to find the right compromise, there were quite a significant number of simulations that were testing different diameters for the north atrium, for the south atrium, and what would be the impact over daylight to find an adequate daylight on the floor plate and the floor area of the building. At the end, it was decided that a floor area with over 80%, an 80% of the floor area with good daylight would be sufficient, as the remaining 20% can be used for the course or for services or for something else. And from there, the diameters of the atrium were chosen and then fed back into the design. So the atriums and the cores are located into the most problematic areas according to daylight, and those were shaped in concrete for structural reasons. This project, I was particularly interested into embodied carbon, which is like the energy and the carbon we use to manufacture the buildings. And that's why, after some research on different case studies, the conclusion was that there's a need to find the right balance in between the thermal inertia provided by the concrete and the embodied carbon in this concrete. And that's why there's a mixed structure of wood, mainly, with the cores in concrete. When it comes to the elevations, there's another potential problem that we find when we're designing, is that the lower we are, the less daylight available that we have, and the bigger that we need the windows. The bigger the windows, the more heat that we lose, and the less comfortable the space. So in order to find the right balance between daylight and comfort, I tested a number of iterations in every floor plate, in every story, to find the minimum window size that would still provide views to the outdoor and good daylight for the building. And those were chosen and designed back into the building. So at the end, the spaces that are designed provide both a qualitative space based on the outputs of all these simulations, and also a quantitative, oh, I forgot that one, dimension of the building we're designing. Here we can see daylight on any given moment of the year and how all the workspaces and the tables enjoy like a fair amount of daylight. And here in the bottom we can see how the building performs naturally. This is a temperature over a typical winter week. And we can see how for an outdoor temperature between 5 and 10 degrees, the design that we have been evolving reaches temperatures almost inside the comfort zone. We would just need a bit of energy during these days that is a bit colder or emptier, the office, to be in comfort. When we summarize these temperature results over a year and we map them into space, we can see for every space in our building the amount of time that space is into comfort conditions, and we can start designing and feeding this back into our design loop. In this case, all the spaces were about 70–80% of the occupied time in comfort naturally, so there was no need to feed it back. And then at the end, that was the conclusion of my design application of our SED simulations. Thank you.
I have a question which relates to the first question I had asked before. That in our program, in SED, we have the dissertations being done individually. And so now I realize that in EmTech and Landscape Urbanism, you can do it as a team. It would be very interesting, very instructive, very informative for me to know your reactions to that. Like, for example, at first sight, it looks like it is possible to do much more if we have a team rather than being able to do it individually. But on the other hand, doing it individually allows you more freedom, like in our case, to choose where you set your buildings and so forth. I mean, could any of you give some comments on that?
Yeah, basically, I do believe that teamwork gives you much more opportunities, if it's the right team, of course. But let's assume that in AA there is always the right team. So in regards to freedom you get, basically different people, they have different interests. So you develop your own interest within the project and you have your own freedom. And by combining these two different streams, you're actually getting different perspectives on a project. Whereas if you develop it by your own, it's really limiting in a way of your vision of the field, of the research you're doing. So yeah, I do believe in teamwork.
Diversity.
Well, maybe you too. If you want to restart, would you want the team or going
I think that throughout the year with the Term 1 and Term 2 project, it's very good to be in a team. Then, given our different backgrounds and how much do we relate to specific climate or context, I think that in our case it's very good to make it individually, though you always have a group or your friends around to check when you're getting a bit lost or crazy into your personal topic. But I found it very better to be individual, to pursue my own interest in this case. So.
I just want to discuss about the issue of simulations. Now that you all have finished, let's say, your projects and you use simulations to produce them, what do you think is the advantage to use simulations? I mean, do you think it's something crucial right now to be part of the design process? Could you do your design without simulations? But that would be one half of the question. And the other, how do you think that changed the role of the designer? No, because in some cases, it seems that, let's say, the conventional role of the designer taking care of every part of the project is not anymore there. No, so what do you see that as a good sign, as a bad sign, or what are your reflections on that?
I'd like to respond. Personally, I think that the role of the designer is still crucial. I mean, I wouldn't use simulation as the only way I see to use simulation is as a guidance. But the more you simulate, the more you learn. So you can basically embody the results even before starting in your own project. As far as you gain more confidence in the results and you're used to read the results, you basically embody those principles. So you, of course, from my point of view, so for thermal and daylight simulation, so for environmental simulation, the principles are embodied in a project even before starting, when you are used to read the data. So I I think that a project guided, a design guided just by simulation would be very, I don't know, very sad. It would lose the poetic, it would lose everything. They need to be a support, not a starting point, I would say.
In a way, also, the more you simulate, the less simulation that you need to do, because you know what is going to happen and you can predict it in advance. Though, when you're trying to prove all the concepts and all the knowledge that you have, sometimes in front of other people or clients, it's better to have like the objective data of a simulation that validates all the principles that you have been putting into the design. So as a final thing of the design, for sure, it's still needed, and as an iteration, it depends on the constraints on the project, I would say.
I also would like to add that, I mean, with simulations too, it's also what's interesting about simulations is that sometimes you can anticipate the results, but sometimes you can't really understand what you get. You get some undesired results, and you start to understand, you know, I never knew this was going to happen. This kind of helps you, it kind of guides what you may decide what you're going to do. In a way, it's sometimes those undesired results kind of make you have a better understanding of the project and how you could better inform yourself what you can do with these simulations, is how I see it.
At the same time, you always, I mean, for us, simulation, not only in our project, but also in the design and build project that we did, you always have to go back to the physical part, because you simulate something and it gives you some results, and then you build it and everything is different. So you always need to have this balance between the physical and the digital. And also, my personal perspective is that there are only so many things you can simulate. I mean, there's some point that some things that can't be simulated. And for me, for example, I don't believe that you can simulate human behavior to the extent that it actually resembles the human behavior. You can do space syntax, you can observe and simulate maybe the flows, but I don't really believe that you can simulate the reaction of human beings. And as architects, we have to deal with that. So, yeah.
We can also talk about what actually simulation is. Like, are we constrained to the computational or digital realm, or simulation can also be a physical simulation, right? So in the case of your tank, for example, that's a physical simulation, and it helps to validate, vice versa, the results that you achieve in the computational simulations, as if I understood correctly. Is that right? I mean, in that sense, I have a question about the physical simulation part, which is that system, like the tank setup and everything, is it scalable to the real one-to-one scale?
So the tank simulation, it's really understanding the materials that you use in terms of like the materiality of what we use, the grain size of the sediments. You know, it's actually different from like the real life river simulation, where in real life the actual clay sediments or the sands, they're actually finer and the rivers are in larger scale. But at least what's really interesting about the physical simulation itself is that it helps us understand how the water actually acts, but in a way that we have to understand like the different grain sizes or even the materials that we use. We need to understand how does that really affect our experiment. And so that really dictates, you know, what can happen in the physical aspect of things. So understanding what we feed into our projects or the parameters that we give it, we must understand all the ranges that we can add to it. So we understand whether it's flow rate, or there's the grain size of the sand. Are we using clay? Are we using sand? Are we using larger rocks? Whatever it may be, we need to understand these constraints, but also possibilities. Yeah.
It should work qualitatively for sand sediment movement, because it's actually quite difficult to scale materials. You would need ultralight material. You would need to work with anthracite or different materials to make sure that they are lighter than what they really are. But it gives you a qualitative idea of what's happening, how deltas form, how to look at nature, how layering of material works if you just cast in section, etc., etc. In terms of water, it works up to 130. So 1 in 30. So you can scale down something 30 times and still measure, and it does still stack up if you do it. It's a bit difficult. It may be difficult because the velocities may be high, so you may end up with waves that span milliseconds as opposed to seconds. But still, if you manage to measure it, it just stacks up to 50-time reduction, or 30 time would be like stretching it over for water.
Wide range of skills and number of software that all of you guys have actually used to produce your research. It's actually a combination of a lot of engineering, a lot of architectural section. Can you kind of comment on how much time, since when did you start actually learning the set of tools that you needed to complete the project?
Okay, I basically learned in the beginning of EmTech. I downloaded Rhino, Grasshopper, and everything here in the computer lab, so you kind of can understand the time limits we had. It's possible.
Same for me. I had never used Grasshopper nor Rhino before starting this program, and in 1 year I learned all the software, so more or less 7 different softwares in 3 months. The first 3 months were pretty intense, but after a while, after surviving to that, we managed to do great things with the knowledge gained in just 3 months, which is amazing.
Well, in our case, getting used to all these gamey side of our work was pretty intense, and we need to find a lot of external sources in order to develop our work. So, for example, self-learning was vital in our exercise, and basically since the beginning, that's why, for example, a big group helped in our case, is because getting used to these new tools, they required a lot of teamwork effort, and that's why it was very positive in our case.
And also, EmTech is a program that gives you hard deadlines. So you will learn the software in 2 weeks. You will experiment a lot. You will have a purpose, and I mean, it's very personal in the end. If you're interested, yes.
I actually have a follow-up question to the landscape project and the physical simulation. I want to know, what level of abstraction is necessary that you can use still as evidence to keep moving forward with your project? Because it's very hard to simulate everything, right, in the physical environment. And it's obviously the level of abstraction is there, but when you're comparing it to the computational models, where is that leverage? I don't know, it's a hard question to ask, or a hard question to understand, but I don't know, is there any reflection on your personal?
I think for me it was more of understanding the behavior of the simulation. It's really hard to say, let's simulate this. This is how the sand dunes are going to move, or this is how the river is going to move, because in a way, natural processes are very unpredictable. But at least what we could use it for is maybe understand behavior and understand what may be implemented and what we could predict and understand more. Maybe that could be a relationship between, I guess, that merging between what we know in the software side, but also understanding things in the natural side, and understanding the behavior is what I think, yeah.
One of the things I noticed that
factor of the environment. But a lot of time, for example, the territory, the morphology of the territory is this comprehensive process with different factors interacting with each other. That's the emergent phenomenon. But since we isolated each simulation, the result only reflects one aspect. And is it possible to channeling all those simulations together in the same platform? Like for example, in a digital simulation, is it possible to channeling all those data together in one platform to simulate the emergent phenomenon of different factors? That's my
question. Yeah, basically, it's always the case that you always need to abstract something, and you never can input everything you even know inside one simulation. It's just not possible, and the more you know, let's say the more software is developed, the more you don't know, and the more things you want to input. So I feel like it's your role as an architect to develop your own vision and your own level of abstraction. And it's your role to say, okay, this is important for me and this is not important for me. But yeah, input everything in one software is not important, not only because of the fact that it will be crazy computationally expensive, but also because it's highly interrelated processes and highly interrelated scales. So you can't really combine global, meso, micro scale in one simulation.
It is also a matter of whether the processes they interact and they are, I would say, co-gradient or co-planar, no? In that we haven't shown, but we've seen some simulations of sand that they are simulated simultaneously with ecology or how plants grow, because it is true in certain areas the landscape is formed by how the plants stop the dunes and they fabricate a different type of landscape. So you could mix many things, but unless you have an intuition that they are actually going to fabricate a new pattern, I think it wouldn't be worth making the huge effort, because you can really get into quite a lot of problem. And I'd like to ask perhaps a question to each of the masters. How do you see the simulation in your role as more of a validating agent, or something that tells you whether what you already knew works or it doesn't work? Or more generative, as a tool that in a way shows you stuff that actually you didn't really know, or you were about to know, but you weren't really there. How do you see the simulation in that sense, in your master and also for personally?
Somehow I think that in SED it depends a bit on the constraints of the site and the program itself. The more complex building or location you're trying to build, the more difficult it is to expect the results and the more generative simulations can be. On easier sites, it's a bit easier to understand what's going on and use them to validate what you can already read from the surroundings and the building you're trying to make. So it depends a bit mainly on the context.
But maybe, at the beginning you may want to validate that you're going to the right direction, but then through the simulation you come across all this data that they're now quantified and you have access to them. So, at some point they do drive your intent as an architect to be based on them to start your proposal, I think.
Yes, in our case, I think simulation tools are more used and more useful to measure what the results are, because basically, as Rafa said, we can always, often predict the results of our simulation when we are used to use this kind of tools. But of course, the incredible advantage is to have proven data and measurable data, so I can say exactly, okay, I'm saving the 20% or I'm saving the 40% in terms of energy performance, or I'm achieving the 60% or 80%. So, I mean, this measure is worth to be used or not. So in our case, can be actually very supportive and generative when we have to take design decisions.
I feel like in our case, maybe because we used a lot of simulation tools and our design actually emerged more from the environment rather than our design intention, I feel like simulations was actually one of the main drivers of our project. And mostly, for example, if you use genetic algorithms, you input conflicting criteria. So you as a designer, you only can put weight on one of those, but you can't really decide. That's why you use these simulations. So most of the times the result is not completely unpredictable, but you really can't do it by your own. So you don't use these tools as a validation tools. And in terms of, for example, robotic simulations, even though it's a physical object and you possibly can predict how it will behave, the result is unpredictable as well, because the way how you can implement all these simulations within the design process, this is the most important part.
Maybe just
I would like to add, because I also use simulations now at work, and I'm very skeptical when you cannot predict the result or predict what will be the direction of the result. I'm very skeptical because at the end we're inputting so many numbers and so many parameters, and if you miss the thermal conductivity of one of the materials, that will lead you like a completely wrong result. So it's always good to be able to predict more or less what will happen, to verify that you didn't like make a mistake in the whole process of setting up the simulation itself.
Just wanted to add that maybe we can also look at it from the perspective of how architecture interacts with different technologies and different disciplines, right? So, for example, we use multi-parameter optimization tools. It's highly situated in biology, or immersive technologies that are coming from gaming, or robotic that we kind of imported from car industries. So these types of different technologies and different, approaches and different disciplines really, I think, opens up new avenues for us as architects in design and fabrication. So I think in that sense it's highly generative, because it allows us to think in ways that we would not be able to without those technologies. So, I mean, they kind of go beyond being just a tool, but they open up, I think, kind of new ideas in our kind of thinking ways as well.
Well, I just wanted to add to this, but precisely on the one hand, but at the same time, it's important to realize that the results from one do not necessarily combine with the results from another. Over the years, there have been many issues. Like, for example, in our field of environmental design, there has been software to do simulation for at least 50 years. And it is the same software, more or less, that continues to be used in different sort of refreshments and extensions. But it hasn't integrated. So when we say thermal, we mean thermal. And it's very easy for somebody who doesn't know the principles to consider that because you're running something which is predicting what appears to be the performance of the building, that it's doing everything, whereas it's only doing thermal, not in this case, for example, airflow or daylighting, which you may need to do separately. And if you do them separately, it doesn't mean that the results you found there, you can feed them immediately. Now, I think the colleague there was asking about implicitly about more integration of software, so that let's have a software that does life, everything. Now, that would be a useless software because it would never run, because it would never be able to fit it enough. So therefore, the simpler the software is, the less it does, perhaps the better, because then very quickly we learn what it does, and it teaches us what it does, and then we can predict its results, and we no longer need it. So then we can go a step further. The other thing is about human behavior, which, as you rightly said, is unpredictable, but it's unpredictable at any given point by any particular group of people. But we can create scenarios about what individual people or a whole group might do. And therefore, simulation allows us, it's the only thing, the only available tool that allows us to say that if people did that, then this will happen to the system that I'm studying by simulation. If they did something else, that this would happen. Now, to the extent that the results might be very similar, then it doesn't really matter what people do. Fantastic result. To the extent that they are dramatically different, then we have to rethink, the whole nature of what we are doing. So in either way, we have learned quite a lot.
Hello, everyone. So the question which I have is, like, apart from the academics, if we come into the real-life scenario, the clients don't usually understand certain terminologies which we'll be using for simulations and all. So how do we interpret that to a client who doesn't have a scientific background or an architectural background to understand that kind of your simulation results or whatever you're trying to do? Because at this point of time, everyone is after sustainable designing or green designing and everything at a building level, but they don't really understand the building physics behind it. So what are the parameters which you think would actually be able to bridge this gap between the client and what we are actually doing through simulations?
For environmental, for SED, clients or regular clients, they care about money. So you have to translate what you simulate and what you care into their terms, that is financial. For example, for offices, when you talk about comfort, you talk about well-being, and you can explain them that 90% of the money spent by any company goes into salaries. So if you provide a more comfortable environment, the people working there will go more to work and will be happier, so the productivity rises. So in a way, you care about comfort and well-being, but you sell it as a productivity for the company that will occupy the building. And when it comes to houses, it's like it will have like a higher rent, or it will be sold more expensive. But clients, or most of them, it's translating your terms into money. It's real life.
That question was interesting, and I just want to respond that because as you are presenting an analysis as a designer, not as an engineer, you are in a way taking responsibility of that analysis is working correct, and by not getting any engineering consultancy, you're putting yourself into risk. So that's actually a good question, because at what point, that's bringing up the question, at what point as us architects should be involved in analysis, and in which point we should give that responsibility to engineers. And because if you try to take all different responsibility in the project, such as structural design, environmental design, crowd simulation in some projects, this will put you in a place that you can't move, and any mistake that you make will both cause problems, such as in walkie-talkie tower, that the shading devices they had to add and cost quite a lot of money. So it's quite a tricky territory. And after that, I want to continue with the question that Simos brought, and I want to ask the students about how you, so two things about a simulation. One thing is justification. After your simulation, how you justify your design decisions, or is it just a validation, or do you continuously get feedback? And if it's a validation tool, how you make sure that your proposal, the action that you made, is the right one? And the second question is about the term abstraction. That actually came to my mind after seeing the CFD analysis on the topography in the landscape project. In which extent that you think that the abstraction of the geometry or abstraction of the local condition is acceptable? And I think that's important because especially if you are working with multi-criteria optimization, in a single criteria, it's acceptable to go into some sort of abstraction because you can see the result directly. But if you are dealing with multi-criteria optimization, the abstraction that you bring for each different analysis model might end up causing a huge conflict and a mislead in the design. So what do you guys think about it?
I would like to respond to the first observation, which, I mean, if you are a professional and you're conducting analysis, you have to trust the results of your analysis. You have to make sure that you chose the right inputs. But, I mean, as an architect, I think I have the same, I'm using the same tools that engineers use. And I learned in a very high quality school. So I do trust the results. I take the responsibilities of the simulation that I do. I mean, I don't see the reason why I should leave engineers do, the same things that I can do. It's not about deciding how to split the responsibilities. It's about what you do. So if you're doing that kind of analysis, you have to trust the results that the simulations are producing. So you just have to make sure that you are doing correctly your job. So I don't see this division of responsibilities between architects and engineers.
I just want to add on to your comment. I think it's really interesting because it's also looking at how we're using these tools that are created from the engineers or these specialists, but it's also seeing it in architect's perspective and how we could use it in our perspective, but also better inform what is useful in our end, but also trying to maybe consult with the engineer and trying to collaborate with engineers, but also using on our end. So we understand like this, almost like this understanding of what is useful for us. And there, in a way, it shouldn't be like, oh, engineer, you do this and I do this. It should be like this collaborative effort, yes, collaborative effort of understanding our perspective, and we should understand their perspective and they should understand our perspective, how we see the analysis, how they help us as a tool.
Yeah, I think that actually this complete separation between architects and engineers is obsolete or should be obsolete. And it's more about who knows and who takes the responsibility for certain aspects of the design. Quite often you can find like architects in a consulting firm or engineers in architectural practice. And the more that we can like integrate both disciplines, the richer the design and the better.
That issue of liability and who takes responsibility for what is actually a quite important one, particularly in the case of simulations that are quite qualitative, like the ones that you've seen of the river model. They don't lead to a design that actually you can scale one to one. But I'd like to see ELU graduates or generally architecture graduates using these tools to understand the aesthetic dimension of the processes they're going to be working with. And then whenever they have to sit with an engineer that is dealing with a re-meandering project, that they actually grab the engineer by the neck and says, actually, I know you can actually obtain this stuff, like, let's push this forward, because I know what are the sort of like effects you can get out of the river. Even though it's true, you could extrapolate your thesis project as for one-to-one, but it fabricates imagination as to how can you just get somebody else's professional squeeze more out of it. Particularly in simulations which are quite difficult to ascertain. You cannot just go back to Lanzarote Island and just test it on straight away. because it's not practical. But I'd like, you know, the students to have that sort of like whenever they go out to practice and they speak with the guys in adult, tell them, look guys, I know what you can help them use.
I think that there are maybe two sides of this. No? Like one is thing that is kind of very obvious right now, that we should work in multidisciplinary things. No? That comes with the idea that whether it is something that who takes the lead on that, or how the different disciplines work together. You know? But on the other hand, and it was a question I wanted to ask, like, because you are using many tools that other people use, no? Like, for example, the girls that did the game, no? And if it's something that, let's say,
happens in reality, and the client wants to do it, why don't they, you know, hire a game designer and not you? So for me, the question is like, well, the architect maybe is using a tool from another discipline to actually brings up a perspective from a different type of problem that the game designers are working on. No? So in a way, it's more taking the advantage of what the technology is kind of providing you, but looking at different lenses, with a different lens. No? I don't know what you think, but that would be probably one of the main points today. No? Like, what are the type of issues, problems, projects that we are or you are interested, no? Like in different scales, in different type of projects, and how the tools can enhance or not to solve, or to at least, you know, propose alternatives for those issues to be responded to.
To have more issues.
Well, in passing, I can say that the tools that we use in SED are all developed by physicists and engineers. But what is very interesting is that all they do is about the architecture, essentially. Yeah. And so there are no apologies for us getting the knowledge, in the sense that when we made the windows bigger, somebody criticized they're too large because there were criteria that were showing that this was bad. Or you make them too small, then there was somebody else who said, no, not good enough, and so forth. So then by using the software now, as I was saying before, we understand the principles better, and also are able to use the same metrics by which we were being judged before, and we were being found at fault. So no apologies. Where's the colleague? No apologies for knowledge, and in fact for taking back what used to be ours.
I mean, I want to add. Oh.
One for you, one for them.
Yeah. Maybe just quickly to follow up on the comment from Seamus. I think it's exactly what you mentioned. Something that was once maybe perceived as the concept of the Renaissance architect, the one who had the knowledge about many different aspects, but at a level where he would be or she would be able to communicate with the other people about the project at its time, comes back with the use of those tools. And congratulations to the students across the programs and the tutors for helping you to tame those tools in those tough deadlines and everything. But at the end of the day, the value comes to the fact that we can communicate not just with the client, which is money-based, obviously, but with the other colleagues, other engineers. And the actual title, there's a title called Architectural Engineer, which is also useful to remember that there is another side of our education as architects. Which brings me to a question which interests me more, because it's all about coupling simulation, physical and digital. And the Tank project in LNU seems to be giving a potential to kind of run parallel. That's something you said that you might do. And since you started very early, a couple of months ago, I wonder, did you ever try the exact same experiment, both digitally and physically? Because I think you captured the digital and then you made it, the physical, made it digital. Did you do exactly the same thing? Or maybe?
Run the same stuff.
Yeah, setting up parameters, yeah, on the software, and then setting up the physical.
Not one-to-one.
Not one-to-one.
What is try the last day before Christmas, doing a rhomboidal shape that he had done in the computer, and it was literally, but I couldn't make it work. But I haven't done it before, but this is just one student, I think is in the back, literally sat down to try to see if it was working, and it kind of did a bit. But I think it would be nice to actually try to validate corners, beats, details. I think the physical one is quite good for details. That in a way you would never be able to check, because there are things that you don't see in the physical, in the digital, you don't see, and suddenly in the physical you see how, hang on, that's jumping, and you would never be able to do it in the digital, because in the digital you don't see things jumping. So there is that sort of like, let's say, typically they would use physical, at least geomorphologists would use physical to make sure that particular aspects are not being bypassed in the digital. But they would never try to match one-to-one, because that's quite a bit of a difficult one. But,
Just one comment on actually your comment. I just thought that these tools are actually some kind of language in which you communicate with engineers, and even if you don't understand them completely as an engineer, engineers can increase the resolution of your project, but they can't lead your project in that particular direction. So when you develop it, you can actually qualify it in terms which engineers will use. So that's why these tools are really useful as this transition, let's say, tool.
Well, in my case, I just wanted to make like a comment on the discussion that we were holding before about the way I think like architects are like using these simulation tools, and I just simply wanted to add like a more critical point of view, because although I think, and I agree with Chiara and I agree with you, like we can be really serious about this, and we can really, so it's my case, so I take it like very seriously when I do this kind of stuff. But if I recognize, and I think we have to be critical about this, that sometimes like we really made a very use this, let's say, of these simulation tools in order to produce very like sophisticated and formal outputs, no? And it's something that we do really well, because in terms of graphics, like we do all this much better than most engineers or wherever, no? So I think that all the tools that we've seen here, okay, are producing like amazing videos and outputs and everything. But I think that in our case and in these programs, and I think that we are trying to do that also in the landscape urbanism program, we really have to make an effort and not just only to focus on, because it's really easy to really go in that direction, no? To focus on producing like amazing and attractive outputs, but also trying to be accurate and serious and really understand, as you were saying before, no? What is really behind in each of these models, no? And I honestly, I know that you have like very tight dates, and or you have to work really hard and learn how to use a software or whatever. So I think that this is something that we have really to take care of. So otherwise we are going to become sophisticated graphic designers, no? So if we really want to keep on playing a relevant role in these things, we are the first ones that have to take this seriously, you know, and also try to be accurate, and also to control the kind of inputs that we, and not to worry that much only about the graphic stuff, no? Just like a critical reflection.
One last.
One last one. See how complex the simulations are, and then I was wondering what would be the outcome of a combination of two studios for a dissertation project.
Very interesting to have, I don't know, an SED student working with an EmTech. I mean, I think personally that would be amazing, the outcome. I remember that, I mean, our studio are very close, and we were always like, there we were going through another studio. Okay, can you teach me quickly these because I need to do the simulation for that. And many times it happened. Many things, not so many, but it happened quite often. And I don't know, I come from a different background. EmTech guys or landscape urbanism, a different background. Crossing our backgrounds or our skills would be quite interesting. Maybe not for a dissertation project, but you can know. Very short-term project together. So I have a workshop.
Yeah, like a one-week workshop. That's super interesting.
But this is one of the problems, I think, the colleague very diplomatically warned against poor interpretation simply by learning the mechanics and running with it. You know, a problem which in the beginning is not important because we allow for that there will be runs and will mean nothing, there will be errors and so forth. But come to the dissertation, we become responsible as you rightly said. And it's only then perhaps that you can bring together from different programs because each of them will have the same responsibility, will feel the same responsibility like the exchange between the engineer and the architect. Whereas before, early on, term one, I think it could be a disaster.
I think it's a matter of having the principles already. When you have learned the principles and modern software, you can validate whatever you could at the end and have a quick workshop and not insert so much. Yeah.
Yeah, charrette.
Like a 1 week project.
Yeah, charrette. You could do charrette.
That's why we organize this event, right?
Yeah, it's part of
overlapping.
Overlapping and
yeah, and I think all the programs have critical thinking to be able to,
Why would you do the charrette with these people? The people were finished.
Yeah, what would you do? Let's say, what things would you add that you didn't do or you didn't study or didn't have access to? What would you say? I would love to have what? A bigger computer, a bigger robot? You know what? Of course, yeah, you can always say a bigger computer, but anything more, or more. What do you think?
Is there a wind tunnel?
A what?
A wind tunnel? Or I saw something there.
I didn't prepare it, eh?
But there is.
No, where there? No, there is no wind. We thought about it, but it's a bit big.
No.
Because, but we thought about it. They didn't have room in the AA for the entire set of monsters. So that thing is biggie, but we talked about it, but it can happen. It should happen actually. This one.
The AA did have a wind tunnel. It was of it 50 years.
You see.
There were tropical studies.
You see. That's such a.
Sometimes it's easier to have a model and with the wind tunnel than build a full CFD.
Yeah, but there are. Javier talks about creating a space where you can have a number of physical models that. I think the physical model gives a certain extra stuff that is difficult to explain, that really says stuff.
Yeah. And it's quicker to change.
Quicker, or it just makes different sense. But,
that is a good addition.
Okay. Good. Good marking. It's really recorded. Okay, well, thanks very much. Thanks everybody for coming. And,